Hi everyone, welcome back. So in our previous lesson, we covered the first part about exponent rules, where we covered a few of the core rules like product law and power of power, and then what happens when we have some special properties. Now, we want to do a deep dive into one more exponent law so that we can fully round out our entire topic on exponent rules. So far we've covered a few things, right? So we've covered when our exponent is negative. And so an example of that would really be when, let's say that we have 5 to the negative 1, right? And we know that we can rewrite this as 1 over 5 to the first power, right? And so our rule is we turn it positive. We turn the exponent positive, and we also write it as a reciprocal. So turn it into a positive, write it as a reciprocal, or just bring it down to the denominator. Generally, in Algebra 2, we just bring negative exponents down into our denominator. In Algebra 2, we might end up, doing some other examples where we're not always just bringing it down to the denominator, but for Algebra 1's sake, generally, let's just bring it down to the denominator. Right, so when we have our exponent as 0, right, so let's say that we have 5 to the 0, right, we know that this simplifies to just 1, right, and I know this because my base was positive, so I know that this is going to simplify to positive 1. If this were negative 5 to 0 power, then I know this would be negative 1, right, so based on the sign of the base, will be positive 1 or negative 1, right? It really just depends on the sign of the base. So if the base is positive, it's going to end up being positive 1. If the base is negative, it's going to end up being negative 1. Okay. For our product law, it was something like this, where we had a to the third power times a to the fifth power. And then this was going to be the same as a to the 3 plus 5, or a to the 8th power, right? And so our rule is if we have the same base, so like in this case, how we had the same base of a in both of our terms, right? Then we just add the exponents. And then finally, we have power over power rule. And so that's something like if we had a to the third power and we raised it to the 5th power, then that would be the same as a to the 3 times 5, which is a to the 15th, right? And so once again, right, we just want to multiply the exponents, right? And so remember, we can prove all these with just a definition of what a power is, meaning repeated multiplication, or when our exponent is negative, repeated division, right? So this can all be proved with expansion, right? This will show us where the reasoning was when we made these shortcuts. So let's look at our first example of our new law that we're going to be covering, which is our quotient law of exponents. And this is what happens when we divide powers. So we're going to use our handy expansion tool once again to help us with this. So let's look at this, right? So we have 5 to the 6 divided by 5 to the second power. And I know that 5 to the 6 is really 5 multiplied by itself 6 times. So that's 5 times 5 times 5 times 5 times 5 times 5, right? And I'm going to divide it by 5 times 5. 5 multiplied by itself twice. Now, when I'm dividing this, right, I see that I have some common factors in my numerator and denominator that I can actually cancel out, right? So I can cancel this one out, I can cancel this one out, and all I'm left with are these 4 5s, right? And so I can rewrite that in exponent form, right, as 5 to the 4th power, because I'm multiplying 4 5s together, right? So 1, 2, 3, 4, so that translates as 5 to the 4th power. Okay, so if I'm looking at my new exponent for my quotient, right, it's 4, and I'm trying to find a relationship between 6, 2, and 4. Well, I know that I can do 6 minus 2 to equal 4. So my prediction is, right, when I have a quotient, right, and when I'm dividing two powers, I'm just going to subtract my exponents. All right, and I'm going to see if that holds true in my next example, right? So we're going into this next example with this prediction that we can just subtract these exponents based on the relationship I saw between my two original exponents, 6 and 2, and the exponent I have in my quotient, which is 4. Let's try this one out, right? So I have 6 to the 7th divided by 6 to the 3rd power. Once again, I'm going to try out my expansion tool, right? So I'm going to try out 6 times 6 times 6 times 6 times 6 times 6 times 6, right? So this is 7 sixes. And I'm going to divide it by 3 sixes. So 6 times 6 times 6. All right, so I know that I can cancel out some of these common factors that I have in my numerator and denominator, right? So I have this common factor, this common factor, this common factor, and all I'm left with are these 4 sixes, right? Okay, so I know my answer is going to be 6 to the 4th power because I can rewrite multiplying 6 by itself 4 times as 6 to the 4th power. Let me look at this relationship between these exponents again, right? So I have 7 as my original exponent in my numerator, 3 as my original exponent in my denominator, and I end up with 4 as my exponent in my quotient, right? So I'm trying to figure out a relationship between 7, 3, so that equals 4, and I notice once again that I can just subtract 7 and 3 to get 4. So it seems like my prediction held true, all right? So prediction was true. I just subtracted exponents. Right? This works mainly because your exponents are really just a count of how many times you're multiplying whatever your base is, right? And so if we're just counting, we said that we only have 4 sixes left, right? And so it makes sense that we can just subtract our exponents to see how many sixes or how many of the base we would have left. So the general rule for the quotient law, and this is something that we predicted, was when we divide powers, we subtract exponents. Oh, yeah. Great, and we proved this using our handy-dandy expansion tool. So let's use the quotient law and actually combine it with some of the other exponent laws that we've covered in order to help us simplify this expression we see here. So I know that I'm going to have to divide, right? And I know that I have to divide because I have this fraction bar right over here. So because I'm dividing, I know that I have to use the quotient rule, right? So if I'm using the quotient rule, I'm going to subtract my exponents and keep my base, right? So when I subtract my exponents, my new exponent for my base 3 is going to be -6. Now, generally, I don't like to have a negative exponent like how I do over here. So I know from my previous lesson that I can actually rewrite negative exponents where I can write it as a positive, right? And then take the reciprocal of it. So I'm going to put it over 1, right? So I have 1 over 3 to the 6, right? So I just use my negative exponent rule, and then over here I use my quotient law, right? And so this is an example of us combining our laws together, right? We use 2 different laws in order to simplify our results. What about when we have different bases, right? So when we have different bases, sometimes we can use the quotient rule, and that's really only if we can kind of change around the base for either our numerator or denominator so that they're the same, right? So let's look at this. We have 9 to the 6 divided by 3 to the 2nd power. Okay, so when I think about 9 to the 6th power, right? When I think about just the value of 9, right? I know that 9 can be rewritten as 3 squared, and I didn't do anything to that power 6, and I didn't do anything to my denominator, right? So looks like I have a common base now, right? And so I know that I could use my expansion tool. So this is really 3 to the second power times itself 6 times. So this is 3 to the second times 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 3 to the second. This is all divided by 3 to the second power. So what I can just do is just cancel out my common factor. So I have this common factor here. I'm left with 5 3 to the seconds, right? So this is really 3 to the second to the 5th power. Or I could rewrite 3 to the second as just 9, right? And so my final answer should be 9 to the 5th power, right? So because I knew that there was a relationship between this base 3 and 9, because I knew that I could rewrite 9 as 3 squared, right? I was able to use my quotient law, even though I had different bases in my numerator and denominator. Let's try out this other example that we have on the side, though. Let's see if we can actually use the quotient law. So I see that my base over here is 3, and my other base is 4. Now I want to think, can I rewrite 3 as a power of 4? Or can I rewrite 4 as a power of 3? So I want to think about it, right? So I know 3 to the first power is 3. That's not 4, so it doesn't look right. 3 to the second power is 9, which is not 4, and that's actually past 4. So I know that I can't rewrite 4 as a power of 3, right? So I know that this option not going to work out for me. Let me try out the other option. Can I rewrite 3 as a power of 4? Okay, so 4 to the first power is 4. That's not 3, so that's not going to work. 4 to the second power is 16. I went past 3. That's not going to work either, right? So I can't rewrite either of these bases in the form of the other, right? And so because of that, I can't use my quotient rule. And the reason being, because I can't rewrite my base in my numerator as the same base in my denominator, right? So at the end of the day, you do need equivalent bases. You do need the same base in order to use the quotient law. That being said, sometimes you might see relationships between the bases in your numerator and the bases in your denominator that might be able to help you out in getting that equivalent base. So I hope that was helpful for you in going through the notes and getting you set up to succeed on your practice problems, right? So if you have any questions, make sure to Google Voice me or email me with a specific example or practice problem you want me to explain, right? Please be specific in the question that you're struggling with so that I know exactly where I can try to help you, right? Good luck.